So this is the first video of the series where I will talk about um, basic group theory. And so I will talk about what are groups, subgroups, cyclic groups, normal subgroups, Lagrange's theorem, then what are group homomorphisms, and then isomorphism. So to start with, let's first start with what is a group. And so let's start with what is a definition of a group. So to understand everything, I think it's important to know the concepts on um, basic set theory, and what are equivalence relations and stuffs like that. So basic relation and set theory will suffice, I think. And anyone studying mathematics, like for first year BSc, should follow this content. So what is a group? It's just a non-empty set. Let's call G be a non-empty subset, a non-empty set such that there is an element, say E in G, such that to start with, we have a binary operation on G. So let's G is a set with a binary operation. So I will just define it as star. So the first axiom says there is an element, let's call it E, such that whenever you operate E on any element of the group from either side, you will end up having the same element A. This should hold for all elements in the set. And secondly, and more importantly, whenever you have two elements of the set and you operate star on it, you should end up in the set as well. Number three, when you have say you have two elements B and C, you operate star and then you operate A. This should be same as this, and this should hold for all the elements of the group. Yeah, so if there is a non-empty set having a binary operation such that this C property holds, and also for any element in the set there is another element of the set such that A star B is same as B star is same as E, then it is called a group, and this is called the associativity property. This is so here this element B, we usually denote it by A inverse, and this is set inverse of A. So every element in the group must have its own inverse, and if in the first property this element, this is called identity of the group, and in any group there has to be an identity element. So let's see some examples. So the first one is when you have only the identity element in the group, there is a group, right? Because all the axioms will be trivially satisfied because there is no element other than the identity. Also, if you take all the real number and the binary operation is just basic addition. So here 0 will be the identity element, and inverse of any element, say inverse of any element A will be just minus of A. And associativity holds from basic addition property. And similar to R, you also have Z, with 0 being the identity and inverse being just the same element with an opposite sign. Right? And similarly, complex number under addition rational number under addition. All of them will be a group. Now, or more, we could talk about more examples. Like if you take all the non-zero real numbers and you take the binary operation as multiplication, then you get one as the identity because whenever you multiply any non-zero number with one, you will end up having the same number. And inverse of any element will just be just the reciprocal of that. And reciprocal makes sense because we are talking only about non-zero numbers. So similarly, q minus 0 and dot will be a group, and c minus 0 dot will be a group. But notice this is not a group. Why? Because say if you take this element 3, and so the property 4 says that it must admit an inverse. So if there is an inverse, let's call it B, then their product should give me the identity element of this group. If it is a group, but yeah. So I'm assuming it is a group. So then this for some B in Z minus 0, but that is not possible, right? Because B will be just 1 by 3, which is not an integer. So this is not a group. Now, another example you can see is if you take all the matrices over any field, or yeah, like R or over say Z or complex number, anything. So yeah, and the operation is addition. Again, for every matrix A, the inverse will be just all the entries having opposite sign, and identity will just be the zero matrix where all the entries are zero. Yeah, and to see more examples, you can talk about all the invertible matrices over serial number of size n, and operation is dot. So invertible means any matrix has determinant non-zero. So whenever you take two matrices having determinant non-zero, their product determinant of their product becomes the product of their determinant, which is again non-zero. Identity becomes sorry. Identity becomes the uh, identity matrix where only so you can denote it as this. So where only the diagonal elements are 1 and everything else is 0. And also the inverse of any matrix will just be the matrix inverse, right? So these are some basic examples of what is a group. And to see more examples, so we'll see more general class of examples. So we'll see. So remember this notation. This is GLNR. This is MNR. This stands for general linear group, by the way. The GL stands for general linear group. And so let's see some more examples. So suppose so I'm assuming everybody knows what is an equivalence relation and how they partition a given set. So suppose you start with the set Z and you define We start with z and a natural number, fixed natural. So we're fixing this. Let's fix this. So you define a relation on z that a and b are related if and only if n divides a minus b. So first thing to verify is it is an equivalence relation. So firstly, a and a are related because since uh, n divides 0. So this means this is reflexive. Secondly, if a and b are related, meaning n divides a minus b, then n must divide b minus a as well, right? Because b minus a is nothing but a minus b with an opposite sign. So this means b is also related to a, which shows this is symmetric. The third one is if AB are related and BC are related, this means n divides both a minus b and b minus c. So it should also divide their sum, meaning it divides a minus c. So it shows that a is related to c, hence this is a transitive relation as well. So this is indeed an equivalence relation. And so this relation partitions the set of integers. So and then we we just choose a representative from each of those equivalence classes and we show that that forms a group. So we'll denote it by n bar. So this is the equivalence class, or maybe I should say k bar because we used n here. So k bar denotes the equivalence class of k. And what are the elements? So let's see. So the way we have defined this relation, k bar means so k bar stands for all the elements that when you divide by n should give you k as a remainder. So this means this should be k plus n, k plus 2n, k plus 3n, and so on. Right? And now, oh sorry, this is not there. Yeah. And so we denote this set of equivalence classes to be z mod nz. So denoting it by this. And what are these elements? This is just the class of 0, 1, 2 up to n minus 1. So there are precisely n elements in this set. Yeah. And why there are n elements? Because whenever you divide any number by n, the possibilities are that there are at most there are exactly n remainders, right? Whenever you divide any number by n. So the remainders goes from 0 to 1 to up to n minus 1. So that's why there are precisely n elements, and the operation is if you take two elements, so we just define it that if you first you do the sum and then you take the class of that element. And look, so to say this is a group, we need to verify those axioms. But before that, we need to also verify that this is a well-defined relation. So things to verify is that this is well-defined. So well-defined means, say, suppose uh, you have, say, if you have a plus b and say c plus d are same, then we need to show that their bars are also same, right? A plus b bar and c plus d bar. But that is obvious. So well defined is obvious. So I'm not doing anything. This is of course well defined. And the identity becomes of course the class of 0, which basically means all the multiples of n if you compare it with this set. So remember, each element is basically a subset of integer. And this becomes identity because, and by the way, I'm denoting it by plus again because basically we're just doing the plus modulo the bar sign above. So this is just a bar, right? And inverse becomes, so inverse of a bar is just class of minus a. So yeah, so under this operation, this becomes a group, and we will define this by z mod n, or sometimes some book referred to as z suffix n. So depends. Yeah. So this is the wide class of examples, and now let's see. So let us now talk about what are subgroups. So observe one thing. You have here say C and addition. And inside that you have R and addition, right? Because everything is same except the underlying set because the operations are the same. The identity, the inverse, all of them are same except the fact that only here we are dealing with complex numbers and here we are dealing with real numbers. And from similarly from real number to rational number, everything is same except we are just taking a smaller set of the original domain. And again, from Q plus, you can talk about Z plus, right? So basically, what we are doing is we are just restricting our binary operation to a smaller set of the original set. And if all the axioms of the group still satisfies on the smaller set, we'll call that smaller set to be a subgroup of the original set that we have started with. So it also justifies the name, right, where we're talking about subgroups. It comes from the subset. It says that given a subset H of a group G, remember group is a set. So assume you have a group or a binary operation satisfying those four properties on a set G, and you have a subset H. If H along with that same binary operation becomes a group, then it's called subgroup of G. Remember, the binary operation has to be the same that of the original uh, group. So, for example, we have already seen R plus is subgroup of C plus. Also, Q plus is subgroup of R plus. Z plus is subgroup of Q plus. Right? So these are some of the examples. Also, one more example you can see that so we have already talked about GL and R, right? So these are all the elements, all the matrices of n size over real numbers that has determinant non-zero. So inside this, we can talk about this special linear group, meaning that all the matrices that has determinant 1. So this is all the elements of GLNR, all those invertible real matrices of size n, whose determinant is 1. So this forms a group again because whenever you multiply two matrices of determinant 1, their product will also have determinant 1, right? Because product of the determinant is same as the determinant of the product. So yeah, so this becomes another example of what is a subgroup. Yeah, and so now let us see some. So remember, all those examples are infinite groups, right? Because all the cell elements, like all the sets have infinite number of elements, countable or uncountable, but still both of them are infinite. And now, and so far we have seen only two examples of finite group. One of them is just this Z mod n, which is precisely n elements, and one is the identity element, which is sometimes called the trivial group. And so, by the way, talking about trivial groups, so every group has two subgroups. One of them is the trivial one and the group itself, because you can talk about the subset to be the entire group itself. Yeah, so these are two extreme cases. Either it is absolutely small, which is just one, the cardinality, and another one is the entire group G. And so, yeah, so maybe from the next time I will talk about some more examples of finite groups, and also I will talk about what are groups generated by a single element, or what do you mean by generator of a group, or how these what is the relation between order of a finite group and any of its subgroups. So we'll come to that in later videos. So yeah, let me stop now here.